Let us consider a conductor arbitrarily shaped, and we release charge Q on the conductor. So there would be some distribution of charges which would be present. And due to the charges which are present, we would create an electric field around the conductor. But the electric field inside is zero, and the potential change anywhere inside is zero. So every single point on the conductor is equipotential. We have seen that before. E would be proportional to the charge we have put in. Let's say we have put this charge Q and we add some extra charge. So that the charge becomes kq, where k is some constant. What we expect that the extra charge we have created would basically go and sit with the same shape which was present before. The distribution will not change. The charge will become more. The distribution between these charges will not change. We have been working completely with linear systems. How the charge is distributed, that would not change, except if I had one positive charge present here, and let's say we doubled the charge, now I should have two positive charges present there. And what would happen to the field? The field, if the original field was E, the field after I have added this charge would become KE, and the potential should also increase by that same amount when I added this extra charge. From this, we can conclude that the charge and the potential are going to be proportional to each other. This proportionality constant is called capacitance. The proportionality constant between charge and potential is capacitance. And its units are farads in SI units. What does this capacitance what is it really doing? Due to this charge, we have this field which is present in space, and we have potential which varies in space, right? This potential is varying in space on a conductor. Everywhere we go, the potential remains the same. By creating this proportionality constant, as we will see soon, what we are able to do is have the space variation converted into a point form. And that point form can go into circuits, and we can put them in a circuit element as a circuit element later. So the spatial variation, which is, as you have been seeing, which is very, very difficult to calculate. And if I wanted to now go and see that I have a conductor, I have connected it to some battery, and I want to see how this conductor shape responds when I change things around the battery. The correct and the full solution would be involving these electric fields and how these electric fields interact. However, as you have been looking at it, that's a very, very difficult problem to solve in general. But if we convert that effect, if we convert the effect of these fields and the potential, then we can basically say, this conductor is behaving like a capacitance C. And this circuit, I can represent it as a capacitor. And I can then go and use what you're learning in DCE 140 and apply it and make our life so much simpler, at least for many applications. That's what we're going to try to understand in this chapter. What is capacitance? How can we calculate it? And then it leads to a specific device called capacitor. Let's take an example. And this is your example one. We have a conductor which is shaped like a spherical ball of radius r. What is the capacitance for this conductor? We release charge Q on the conductor, and as we know, the charge is going to be uniformly distributed on a sphere, and electric field anywhere outside a distance r is simply kq by r square r hat, and the potential V on the conductor is kq by r. Potential anywhere inside is also kq by r. What is capacitance? Capacitance is q by v, v being the potential of the conductor. And if you can calculate potential at one point, potential on the conductor would be the same everywhere else. And if we just substitute the value of V's, Q's and Q's will cancel out. And when Q's cancel out, all we would be left would be R by K, or K is 1 by 4 pi epsilon naught. So we can write this as 4 pi epsilon naught R. That becomes the capacitance for the conductor. Please note, what does this depend upon? This completely depends upon the geometrical properties. The shape of the conductor, the size of the conductor R, and it depends upon the material surrounding the conductor. So this capacitance we are calculating is a geometrical property of that conductor. The shape, what epsilon material is surrounding it. It is that the geometrical property is spread over space. We have converted that spatial nature into one single constant. How this helps us will become clear in the next section.